Hello everyone, this is Kevin Hull and I have with me Austin Langvenis this morning. We are going to present to you a solution for surface compensation, typically used on 3D printers or other CNC applications. So without further ado, I will hand it over to Austin.
Good morning everybody. So like Kevin said, it's a solution used for 3D printers or CNC applications, but it could be expanded into a different application depending on what solution needs to be provided for that application. It's mostly about measuring a surface and providing a real-time offset to an axis position. So we'll start with an overview. The purpose of this solution is to measure variations in your surface. So many surfaces that you may have on your machine aren't perfect. I don't think anything in life is perfect, although we tend to like to think we can make things perfect, but in reality they're just not. So in order to compensate for that, we have a solution that we can take several data points across the surface and measure the displacement from your tool point to the surface, and that data can be used to interpolate a real-time offset and be applied to your mechanism in real time. So to implement this solution, we've created 4 function blocks. These function blocks reside in the Group Toolbox, and there are 2 main function blocks, what I call the core. Those are GridMeasurement and GridControl. GridMeasurement is the function block that ideally you really only have to run one time for your machine, and after that one time you can use it for the rest of that machine's life. Only time you would run it again is if you maybe upgraded to sensor or put a new surface on the machine. After that, we have GridControl. This is the function block that is actually controlling your external axes that need the offset applied to. After that, we have read and write grid file. These are 2 secondary function blocks, I call, that are just used to save grid files onto the flash memory of the control. So let's take a look at a picture here. So this is a surface. Hopefully your surface doesn't look like this one. Pretty bumpy, but we could use grid measurement to take several data points along this surface, and we can actually apply an offset based on those divots and the bumps on that surface. So if grid measurement worked perfect, you could run it over across this surface and print something. That would be pretty hard with grid measurement on that bad of a surface, but ideally it could be done. Here's maybe a more practical example, that you have a wavy surface. So if you have a large bed, there's a chance that there's warping in it, and not all points in it are at the same height or at the same level across the entire surface. So grid measurement again could be used to take several data points across that surface and account for that waviness. So as I said, the core function blocks, there's 2 of them. Start with grid measurement. Here's a picture of the function block. What it does is it measures the displacement from the tool to the surface in a grid pattern. You see we have 3 var inouts there. There's the axes group. I like to refer to this as the control group. It's the main group in the system, and it contains most likely real and a virtual axis. The virtual axis in most applications will be your z-axis, and that z-axis position is then used to control the real axis position in another group, which we'll get to, along with the offset applied. After that, we have grid setup and grid results. Grid setup is only used for grid measurement, just setting up the parameters of how you want to be measuring your bed, such as speeds, positions, measurement method. We'll get to all of these things in the coming slides. The next core function block, GridControl. First thing I'll mention here is that there's a virtual group and a real group var in out. The control group, as I said, that's your main group. It may consist of real and virtual axes. After that, we have the real group, and I've named it my var in out variable comp group, and that's short for compensation because this group will have the axes that we want to add compensation for. So with my bullet points, as I mentioned, GridControl actually controls the real group via a Y group direct control function block inside of it. It calculates the position offset based on your measured data, and then it will apply that offset by adding it onto the virtual axis position from the main group, and then inputting it to the commanded position of the real group. One thing to note is the grid results structure that you have on GridMeasurement must be the same grid results structure on GridControl, meaning it should be a var global. We have two other var and outs that I haven't mentioned yet, and that's pendant data, user app data. These two var and outs don't necessarily apply to this application, so I won't be speaking much on those two var and outs. But you should have them connected so you don't get compile errors. The last thing I'll mention is in the bottom right of GridControl, we have the output grid offset. I'll mention this later as well, but grid offset should be a var global. So I want to speak a little bit more on GridControl first before we get into grid measurement. The reason being because GridControl must be running before you run grid measurement because it's actually controlling your real axes. But this is actually sort of step 2 in the process. Grid measurement would be step 1. As I mentioned before, there's two groups. The virtual group, as I said, can be made up of real and virtual axes. Here's a picture from the hardware configuration. As you can see, I just have the z-axis with a virtual axis. There's the real group. It's a custom group, whereas the control group typically would be a gantry. The real group can have just one axis, or it could have a secondary axis, being a prime. GridControl controls the compensation group. And then it takes the virtual group Z position and adds the offset to it. Then it inputs it to the real Z-axis position in the compensation group. One thing to mention, this offset is applied in real time, so there is no delay to your axis position. I mentioned it later on in the slides that you'll want to have GridControl running at the MeasureLink rate cycle. So in a task, set to the same rate that you set your MeasureLink rate in your hardware configuration. So now we can get to grid measurement. This is the most complicated part of the solution, whereas there are a lot of parameters that need to be set, and you need to know what you're doing before you start, especially if you're using one of the three methods that we support, which is torque, and torque measurement will actually come down and touch the bed. So as you can see here, we have an example grid. This grid would be laying along your surface that you want to measure across, and it will take several data points. So in this case, we have a resolution of 4, giving us 16 data points. One thing to mention is you can set the resolution specific for X and Y. So if you have a rectangular bed, you may want to take more data points along Y-axis. So you'd want to set that to maybe 8 and your X to 4, giving you more data points along the surface, but at a uniform spacing compared to the X. So for grid measurement to be applied properly, there's a specific point at which your real Z-axis needs to be zeroed at. And that is at the first measurement position of the grid. This measurement position is specified by setting your grid setup.min corner. It's an array of 2 L reals with index 0 being the X position, index 1 being the Y position. This is essential for getting the solution to work properly on your machine. Here's a GIF file of grid measurement running on a machine. Wanted to show this example so you have an image of what exactly it's supposed to be doing once it's running. This type of measure method that it's using is analog, and analog provides the fastest measurement method that we support. The reason being because it doesn't need to move down in Z until a trigger is sensed on the controller. That trigger could be a proximity sensor or your torque limit value that you set in the grid setup structure. The analog is nice though because it's always providing an input to grid measurement that it can just go to each XY location, read the measurement quickly, and move on to the next. It can also be done at much higher speeds. You may be wondering, well, if we're only measuring a finite amount of points on our surface, how can we calculate an offset for the points we did not measure? I won't get into too much detail about this, but I thought it would be useful for the user to know how are we coming up with these values. We're not magicians here, we're engineers, so we're not just pulling it out of a hat. We use a bilinear interpolation calculation, which takes 4 points and interpolates in between all 4 of them to calculate an offset. It's rather reliable because it's interpolating along 2x axes or 2x positions, and then between those it takes the result and interpolates between the y. So that, as you can see, it would first interpolate between x1 y1 and x2 y1 and we'd get the result of r1. After that, it goes between x1 y2, x2 y2, gets the result of r2, and then it interpolates between r1 and r2 to get the final result of your offset. This offset would then be added onto your virtual axis position, as I've mentioned several times now, and then input to the Y group direct control for your custom compensation group. Here's a quick function block diagram of the process that it's taking. It takes the current X and Y position, runs it through the bilinear interpolation, and output is your offset. After that, you have your commanded Z position on the virtual axis. You add the grid offset, and you have your compensated position. So now I'll get into some methods of measurement that are supported for the grid measurement function block. We have the analog input, as you saw in the previous slides a couple ago. That's using a laser or LVDT. This is connected to either an LIO option card or SLIO input card. The variable is used as a var input to grid measurement. It's the only one that has its own var input for grid measurement. The other 2 measurement methods are set up in the grid setup structure. The third bullet down, we have GTP MeasureMethod, # analog. That's the enumeration that we can use to set grid setup.MeasureMethod. The next measure method would be digital input. It's a proximity sensor that must be input to the servo pack CN1 connector. Inside of grid measurement, it will use MC touch probe and wait for the trigger of the sensor, record the position, and move on to the next point. We use grid setup.digital trigger to initialize what sensor or CN1 input we'll be monitoring. Again, here's the enumeration used by Yaskawa for setting the grid setup.MeasureMethod. I hope the quality is okay, or that you can see the GIF on this page. If not, then I recommend going back to the YouTube video once it's published to see these GIF files that I've attached to my PowerPoint, and it'll give you a good interpretation of what grid measurement is doing. The last measurement method is torque feedback. It's the least recommended of the 3, whereas it takes the longest time to set up, and there are also safety concerns that need to be taken when you're using this method of measurement. The reason being because your tool is actually going to be coming in and touching your bed, and you don't want to ruin your tool by pressing too hard into it, or your surface, or worst case, both. What torque feedback measurement method does, it's the most complex of the 3. It will set the torque limit of your servo pack for the Z-axis in this case. It'll either be PN402 for positive torque or PN403, negative torque. If your torque is decreasing as you get closer to the bed, then PN403 will be set, and 402 will be set if it's the other way around. So, as I said, this is a tool point surface contact, and it's It's going to come down and ideally just gently touch the bed. It will hit its torque limit and record the position of the axis. If anyone has any questions, feel free to input them to the webinar. I'd be happy to answer any questions that you may have. So let's dive a little deeper here. First step, as I said, is grid measurement in the whole process, and you're going to want to set up the structure for it, which is grid setup. As you can see, there's a lot here. It's not too complicated, but again, there's a lot that you need to know before you get started using this solution. We'll start from the top of this. We have MeasureMethod, as I mentioned on the last slide. After that, measured plane. Typically, this would be your Z axis. It can be supported for measuring a different degree of freedom. I would suggest contacting Yaskawa in that case because most of the testing has been, actually all of it, has been done for a Z-axis. The input to that measured plane is just a string. So typically it'd be just your apostrophe Z apostrophe semicolon. Easy as that. Your external plane, that is the axis ref number of your real Z-axis. Grid setup needs to know the real Z-axis ref so that it can read the torque of it. Or if you have the digital input, then you'll be wanting to read the digital trigger ref for that servo pack. As you can see on the next input down, there's the digital trigger, which is data type trigger ref. That's the same data type that is used for MC Touch Pro. I'd suggest referring to that help document for setting up your trigger ref and for the correct CN1 input that you'll be using. If you're using torque, then we have grid setup.torque limit. This is a dint. It's a dint and not a floating point number because it's setting the PN number on the servo pack, and that is an integer value of % of rated torque. To set this number, you'll want to take some initial logic analyzer traces to determine what your torque is when you're actually touching the bed or the surface. After that, we have setting up the actual grid that you'll be measuring across. I have a large picture here that can be found in the grid measurement help document in our toolbox manual. You have your min corner out to your max corner. Max corner is either going to be where you end at, or it could be where you can either end at the max corner or on the other side of that same row, as it takes a zigzag pattern throughout the grid. The next in the grid setup is the resolution. In the grid here, example, we have a resolution of 10. The resolution should be set according to how imperfect or how much variation is in your surface. If you believe there's a lot of variation in the surface, then you'd want to maybe set it to 10 or even the max supported of 20. The resolution can be increased past 20 by modifying the grid setup structure in the Group Toolbox. Don't hesitate to contact us at Yaskawa if you need help modifying your resolution. We have taken files where it had a resolution of 100. Luckily, they're using the analog measure method to make it so it didn't take a full day to take all the measurements. Whereas if you're doing torque measurement, there's a good chance it would. Instead, using the analog method, it only took maybe 20 to 30 minutes, if that. So again, to reiterate this, the resolution can be set as low as 3 and up to 20 or more if you'd like. And that is all determined based on how much variation is in your bed. I'd recommend going small first, depending on your measure method, and increasing it if you're not getting the results that you expect. So the final stuff of grid setup is what we can refer to the images that I've enlarged on my slide here. We'll start with the position values. We have transfer position, approach position, and measurement position. If you're using analog, you'll only be at the transfer position. For digital and torque, you will be setting the approach and measurement positions. The transfer position is a height that is a safe distance away from the surface that you can move to the next measurement point. The measurement and approach positions are much more critical in your setup, as you want to set your measurement position to the point at which you expect either your torque limit to be hit, where you're actually touching the bed, or in another case where your proximity sensor typically triggers. The intermittent position is the approach position. So coming down from transfer to approach, you're at a medium velocity, whereas transfer would be high and measurement would be low. So you come down at a medium velocity, preparing to start waiting for your input to be triggered. Once you've reached the approach position, you slow down to a slow velocity, and at which point grid measurement is waiting for your sensor or torque limit to be triggered, at which point it would record the position. The tolerance is the most critical of all of these settings, as it is user defined and it is an amount above or below your measurement position that you deem is acceptable for measurements. It can also be used as a safety mechanism, where if you had a tolerance below your measurement position that you know your nozzle or tool point is touching the bed, but it hasn't read its torque or hit the torque limit yet, it will then produce an error and restore its torque limit and move back up, at which point the function block would be in an error state and needs to be re-executed. On the other side, if your measurement point is at one location and your sensor triggers, or your torque limit is met at a value outside of the tolerance above the measurement position, it will also error out and do the same. So I've mentioned mostly about the positions here, but there are also transfer, approach, and measurement velocities. The transfer velocity can be a higher speed. Approach is a medium speed preparing to move into the measurement position, and then the measurement velocity is a slower one that is acceptable for reading an input. These are all user defined, as I said before, and testing may need to be done to determine what those values should be. They're all machine specific, but typically it would be measurement position or velocity would be between 1 and 5 millimeters per second. Approach velocity could be between 5 and 20 millimeters per second, and transfer velocity could be anything above that. Although if you're using analog, you want to make sure that the transfer velocity or your acceleration, which can be set in the grid setup structure, isn't too high where you're not able to come to a complete stop or stop long enough at your measurement position. Here I want to show some examples of the initialization of the grid setup structure. As I said, there's a lot of depth to it. There's a lot of stuff in it, but it can be broken up into sections that are easy to manage. As you can see in this example, I'm measuring the Z-plane. I'm using digital MeasureMethod. I've set my trigger ref.bit to 1 as I'm using the ZSI4EXT1 input on the CN1 connector of the servo pack. These bit values can be found in the MC Touch Probe help manual. A good thing to point out here is I have external plane defined, and I have 2 axes on it. That is because in this example there is a Z prime axis, a secondary axis configured inside hardware configuration. One thing I didn't mention on the last slide, since it wasn't shown on the picture, is there's a max deviation. This is a deviation between 2 measurements that is acceptable based on a user-defined acceptance value. So it won't error out as tolerance produces, but it will at least give you a warning saying 2 measurements were this far apart, which in this case, if one measurement was 2.5 millimeters away from the previous measurement or any of the other measurements, it will produce the compensation warning on GridControl, just letting the user know that 2 of the points were quite far away. In this example, I also have a measurement position of 2.5. This is the position that I tested and found that my proximity sensor typically triggered at. I then set a tolerance of 3.0, mainly being because I wouldn't want my machine to run further down in Z past negative 0.5. But if a measurement was taken at above 5.5, then the tolerance error would also be triggered in that case. Here's analog measure method. This is the full setup here. As you can see, there's a lot less because it only needs the transfer velocity and position. The approach and measurement position and velocities are not used for analog. You can see that my transfer position is a lot higher than the digital position that we had for measurement position, and that's because the laser has a lot more range of being able to read a position value. Next is torque. The thing that torque has that the other two didn't is the torque limit. In this example of initialization, I'll be setting PN 403 to 1% rated torque when it's taking its measurement position. When it's taking the measurement and moving into the measurement position. So it sets the PN 403 and then also is reading MC read actual torque and waiting for it to the output of that to hit 1. At which point it records the position and moves back up. After each measurement is recorded, it'll briefly set its torque back to the original torque you had prior to starting grid measurement. So you don't need to worry about your torque limit getting set to 1 and having to go back to hardware configuration to reset it. Torque measure method, as you can see, my measurement position is negative 0.5. So I've zeroed my machine at a specified location, at which in the top right you can see there's a specific location that my machine needs to be zeroed at. I mentioned this a couple slides ago, and that is at your min corner. That is because all of the data is normalized to the first measurement. So my measurement position is negative 0.5 as I expect to move into the bed. I would recommend having a tighter tolerance on torque measure method. I have a tolerance of 3.0, but I would recommend something tighter than that, maybe 0.5 to 1. As I said, torque is the most complicated and least recommended of the 3 measure methods. So I wanted to show a logic analyzer trace. You'd want to take a logic analyzer trace before you start your grid measurement to determine what you should set that torque limit to. In this logic analyzer, you can see, first of all, I'll mention that this machine was not zeroed yet, but it could still be done after grid measurement has been completed. That is because the grid results will normalize the data, but once it's actually being used in GridControl, then that's when your machine must have been zeroed at the correct location. So at this point where my cursor is located, that is where the machine was touching the bed. So you can see it was hovering between 3 and 5, and then once it started touching the bed, the torque hit 2 and briefly paused, took the measurement, and started its move back up after restoring its original torque. Another example, this one nicely shows the torque getting restored back up to 20, or the range of 15 to 20, but the torque graph here clearly shows that it decreased significantly, and at which point the position was not changing because it didn't have enough torque to push any further into the bed. So we took the measurement and proceeded on to the next measurement location. So by this point, you should have the knowledge you need to apply grid measurement onto your solution, into your application, and run it until it's done, at which point you'll be left with some data. This data can either be saved into a CSV file or just marked as retained. These are the 2 function blocks, read and write grid file. The file name is user-defined. It's stored on the controller's flash memory, flash/local. It will be given a extension of .gmd. It's not required to read or write the files because it's just recommended you set your grid results as a retained variable. Here's our cursor here. I haven't been moving it too much. So we have a question. Is the measurement done with respect to MCS or ACS? The measurement would be taken with respect to MCS positions, as the group is set up for a gantry in my examples. Torque measure method would require a gantry, but the analog or digital measurement methods could be done with any type of group or mechanism type that you have. If you do go the route of saving the data into a CSV file, here's an example of what you'll get. The biggest reason you'd want to save a file is if either you're changing between data sets or you are having to cold start your machine, which means you lost your retained data in the grid result, or you're just using a different controller, some other situation where you are unable to access the retained data and you've lost it. So it's always safe to execute write grid file after grid measurement has been executed and completed, so that you can always come back and execute read grid file and come up with the same data that you had from the one time, ideally, that you ran grid measurement. Biggest thing to note, I keep wanting to say this as a warning, that our first measurement has been set to 0 because that is where your machine z-axis should have been zeroed at, meaning there is no offset to be applied at that point. We know that there is no offset to be applied because we've set the 0 there. Other goodies in the CSV file, on line 1, it's a version number that is used for internally within read and write grid file in case we decided to change the structure. After that, line 2 is just a header row specifying what line 3 is. As I've said, we are pretty much at the point where grid measurement is applicable now and able to be completed. We have our grid results and we want to move into grid control. This is actually using the grid offset in real time and compensating for your surface. Some stuff I've talked about already. We have our control group, compensation group, and we have the real axes along with one virtual axis in the control group. The compensation group has a Z and Z prime. Grid control controls the compensation group and applies the offset to the virtual axis command and position. And the biggest thing to take away from this slide is the output of grid control has grid offset and it must be marked as var global. I thought this would be worthwhile to show that we have 2 groups in my hardware configuration here. Control group is a gantry, but as I've said, it does not need to be a gantry unless you're using torque measurement method. Here's my compensation group. It's a custom mechanism type containing just one joint of Z. I made the label Z. It's not a machine coordinate label that was made because it's a custom group and it has no machine coordinate system. So that I wanted to just kind of explain more about that, how I said that MCS is the coordinate system primarily being used. That's for the control group, but the compensation group only is made up of one joint, so it just has its ACS. That ACS is used for the Y group direct control, controlling this custom group. Inside grid control, we have sync servo to virtual group. There's a future webinar planned on this topic because there's a lot to it, and we are not going to get into all those details. But it's worth mentioning because we need to use it. It manages the synchronization of our virtual group and the real group. Again, the virtual is our control group, the real group is our compensation group. Stub function blocks live inside sync servo to virtual group. And these stub function blocks need to be copied from the Group Toolbox and pasted into our application program. UserGroupPrepareEnable is the function block that will actually have an MC power and reading positions and setting positions to synchronize the real and virtual axes. The reason we need to synchronize before powering is because we wouldn't want to input a virtual commanded position that is not the same or very close to the real position. If they're out of sync, it would cause the real axis to attempt an instantaneous move to the virtual axis position. So before Y group direct control is enabled, the positions need to be synchronized. The other stub function blocks we have are the custom joint command, custom inverse kinematics, and custom forward kinematics. These provide the relationship of taking the virtual position and adding the grid offset to it and storing it into a position vector for the real axis to be controlled by the Y group direct control. Here's an example of what your stub function blocks would look like for these custom function blocks. The reason we need grid offset to be a var global is because it is used inside these stub function blocks. Custom inverse kinematics would be used for an MCS. So if you're using a GUI that supports multiple coordinate systems and you're an MCS, you'll have sync servo to virtual group using the custom inverse kinematic. If you're an ACS, it'll be the custom joint command. And the custom forward kinematics is used just to set the virtual position when you're changing between coordinate systems. In that case, we'd want to subtract the grid offset. In the other two cases, we add it onto the virtual position. In custom forward, we subtract it from the real position. This is what your UserGroupPrepareEnable stub function block would look like. There'll be an example inside the UserGroupPrepareEnable inside the Group Toolbox for your use for easy setup. What we have is powering the real axis, reading its commanded position, and setting the virtual axis to that position. I want to note that if we are setting the position of the virtual, that we are just tagging it from the axesgroup.axisref. So let's I have my live demo coming up on my last slide here. So we can just hop in there now actually to show why I chose index number 3 for this axis ref position. I chose index number 3 because it is the third index in my control group. If I had a secondary axis for X, this would now be 4. Added a secondary for Y, now this would be 5. And that index would be used on this MC set position. If it's not set correctly, there's a good chance you'll be setting the X or Y axes in your control group instead of the Z. My demo, I just want to kind of show in real time how the positions are correlated, show when the grid offset is not applied, meaning you have a compensation warning and your machine is moved outside of the range you've measured. We'll also see how the virtual position won't change, but the real axis positions will be, because the grid offset is always changing if you're moving in X and Y. Something to note, very important also, is the task settings that you have for these function blocks. Grid measurement doesn't need to be at a Mechatronic cycle rate. It can be at a medium or fast task. I'd recommend between 8 and 20 milliseconds. Grid control does need to be run at a Mechatronic cycle rate because of the wide group direct control living inside of it. You want those positions to be updating as fast as possible for your real axes to not lag or have any latency behind the virtual position. Read and write grid files can be run in a slow task. We recommend a slower task because it will help prevent any watchdogs from occurring when writing a file. A watchdog is unexpected though because the files are rather short, unless you have a high resolution, such as 100. So I'll come over to my live demo. In my watch window, you can see I have my offset and my virtual position, and my two real axis positions. You can see they're not the same, and that's because I have a grid offset of this small decimal value. I'll bring up my GUI, and I'll show you first if I go to my first measurement position, which was x -10 and y -10. That, as you can see, I'm jogging z-axis right now, and they're all moving synchronized together. If I move my x-axis, the virtual axis position is static right now, but the real axis positions are changing based on my grid offset value. I can move in y as well. Move my y-axis as well. You can see the grid offset is changing no matter which way I go. But if I come down here so you can see my position values, if we move, let's go in y. If I move y past -10, now you're going to see that no matter which way I move, my grid offset is not going to be updated unless I get back in range. You must take this into account when you're running your machine, because the grid offset will just take its last known value, but it will start updating once you get back in range. If we move outside of the range, we'll see the grid compensation warning here, and it is reset when we get back in range. Now I should be able to, does not want that. Okay, well, what I wanted to show there all was just that if I move to my min corner of -10, -10, my grid offset would be set to 0.
Okay, Austin, thank you very much for a very comprehensive explanation of the surface compensation solution kit that we have in the Group Toolbox. One thing I think that was interesting that you pointed out early on in the presentation was the fact that even though the large portion of the setup is grid measurement function block, that the first thing you need to do is enable and run the grid control function block. And that's because of this dual group solution. And even during the measurement taking process, grid control can actually physically operate and move the real servos along the way to do those measurements.
Right.
So I imagine if you could show that slide again.
Yeah.
There was a VAR input on grid control to essentially disable the correction.
Yeah, right. I've got it right here actually. That's one thing I actually did not mention, is that if you have grid results and say you don't want the offset to be applied in, say, manual mode of your GUI, then you can have disable compensation be turned on and the grid offset will be set to 0. Another case where the offset will be set to 0 is, say you've already run grid measurement once, it has data inside of it, but you go to run grid measurement again. You don't have to disable the compensation in this case. It will already know internally that grid measurement is running right now and I don't want to apply an offset, as that would just skew all the data.
Does this have application outside of 3D printing? And I think that it can. It might in any situation where there's the need to compensate for an imperfect surface, whether it be wood routing or otherwise.
Right. Yeah, I actually mentioned that right at the very beginning, that this webinar is titled for CNC applications and 3D printing, but it can easily be applied to probably anything that you may have that can measure a surface.
And some of the techniques that you've seen here towards the end of the webinar, you'll see again in a future webinar more on the subject of other solutions, these sync virtual group to real axes function blocks used in other applications besides doing the surface compensation. So they have a wider reaching functionality, really, and also enable us to operate the system from that front-end GUI you saw. That will also be coming out probably early 2020.
And see a question about the sending project example. I can surely send you this project as an example, and it would be a great starting point for anyone that's looking to apply this solution. At some point, there's a chance that we also publish it on the Yaskawa website. Are there any more questions? If not, thank you all. It's been a pleasure, and I wish you luck if you use this application. We're quite proud of it here, and if you have any questions from here on out, don't hesitate to email myself, Austin Lang Venice, or Kevin Hall, and we will be able to help you out. Thanks, everybody.